Okay, guys, in this segment, we're going to talk about gases and kind of how they are unique to our states of matter. So here we go. So first of all, have some unique characteristics to them. So first of all, they're the only state of matter that is able to completely break free of intermolecular forces, or IMF, under ideal conditions. Okay. So unlike the other two, where they actually were bound by IMF, gases are not. Gases are also so very far apart that the size that they have and their mass doesn't really matter in terms of how we view them. So basically, we don't care how big they are anymore. Because before, with solids and liquids, the size of them affected their melting points and affected the viscosity and that kind of stuff. So for gases, the size of the actual particle no longer plays a role because they're just too far apart for that size to actually change anything. Okay? Now, because of these two things, gases are able to expand infinitely. Okay, so they can keep expanding until they hit something that stops them. So basically, the walls of some sort of container, or the walls of a room, or basically, if they get out of a building, they basically can hang out anywhere they want to. They're only held by gravity. Okay, what makes gases also very unique is that they're compressible. So you actually can take a gas and compress it down and pack it in really tightly, or you can open it up and let it expand to fill its containers. We use this principle a lot with gases to actually transport them and to store them and then to use them. For example, like in your grills in your house, if you have a gas grill, when you go buy the fuel for that, you buy liquid propane. Well, they call it liquid propane because they compress the gas so tightly that it actually reliquefies it in the container. Okay, and then as you use it, you release the valve and the gas is allowed to leave. So as it leaves, it expands, goes back to its gaseous state, and then you actually burn it as a fuel for your grill. Okay. Also, interesting enough, something that people sometimes don't think that much about is that gases are able to flow just like liquids are. Okay, and we use that principle to run leaf blowers, to use air hoses to fill up bicycle tires and car tires, that kind of stuff. We push gases through pipelines to run your natural gas, stove, or to run maybe a gas furnace, those kind of things. So this ability to flow like a liquid is also a kind of a key piece of gases. Okay. Now, gases are actually dependent on 4 different variables. And if you take a look, pressure, temperature, amount, you might as well write the word moles right here because amount is a measure of moles. So basically, we're dealing with moles and volume. You'll notice there's something very obviously missing from this list. So if we're going to measure what a gas does and how it works, we can deal with its pressure, its temperature, its amount, its volume. But notice how we don't care what it is. Okay, so the actual type of gas or the formula does not matter. Now, at first glance, you may be like, wait a minute, how's that possible? Well, let's go back up to our parameters up here. If there is no IMF, we don't care if it's polar or nonpolar, right? If they're so far apart that size doesn't matter, well, we don't care if it's a big molecule or a small molecule. Mass doesn't matter, well, we don't really need the molar mass for that. So really, all those things that make gases unique in terms of the physical world aren't really a role here. Now, obviously, different gases are going to chemically bond differently, but we're talking about the variables in the physical world now. So things that are going to change how a gas acts physically, not chemically. We dealt with chemical type stuff in a previous unit. Okay, so gases are very different than other substances, and one of the reasons why is because gases actually act on this idea of this kinetic molecular theory. Okay, so what we're going to do is we're going to jump to another little presentation that we have that we'll see later on, and we're going to talk more about kinetic molecular theory. So same basic notes as before, but we want to add this little piece of kinetic molecular theory. Okay, so kinetic molecular theory basically is the explanation behind how kinetics work within a molecule or how gases move basically. Okay, so things you think about. Gases are moving rapidly in constant linear motion. Okay, so high speeds, 100,000, 2,000 meters per second, straight lines. Okay, they can change direction, but they have to hit something. Okay, so imagine like gas particles bouncing off the containers of a wall. Sometimes I say imagine like a puppy on tile floor or like a puppy on like a hardwood floor. They can go straight, but for them to stop and change directions, they got to run into a wall, bump into something to get them to change their directions. They're not really good at turning on those kind of things. Okay. Another example is maybe like think of like a billiards table or a pool table, where if you're just throwing the balls around on top of the surface of the table, they can bounce off each other, but they always move in straight paths. okay, as you go down the table. Now that's assuming you don't put spin on the ball and all that jazz that fancy people can do, but we're not fancy, so they go in straight lines, okay? So example here, just moving the balls around, bouncing around, that kind of stuff, okay? Now, the last piece of this puzzle is that gases have to act ideally, okay? And that goes back to some of those things we've already kind of discussed, where we're going to talk about elastic collisions, so there's no energy loss in that. We're going to say that there's no attractive force, so we ignore IMF. They're just too far apart. They're moving too fast for that to happen. We're going to say that the particle itself has no volume, okay? So we don't care if it's a big molecule or small molecule. It doesn't really matter because those particles are too far apart. Okay, so these ideal conditions for our gases, okay, collisions are elastic, no attractive forces, no volume. They work great in our world because ideally in our world, our real gases that we have, because when we really deal with them in a real lab kind of scenario, we actually have temperatures and pressures that allows them to act under these scenarios of being ideal. Okay. Now we can change that in a lab setting, or actually in a manufacturing industry setting too. We can change it so a real gas doesn't act ideally by changing pressures and temperatures. But that's more of a topic for our next unit, which we get to more depth of how we can manipulate gases and what they do. Okay. So that's just kind of a little look at how gases work and how they are. That's this segment. Thank you.